Okay, welcome back. And today we start Chapter 10. And Chapter 10 is now expanding the hypothesis testing to testing involving either, two populations. Okay, so we're going to be looking at hypothesis testing involving two populations. So in this chapter, we're going to discuss hypothesis testing involving two means, so the difference of two means, or two population proportions, and where we're going to look at the difference between the two population proportions. And so everything that we did in Chapter 9 is now going to be expanded to two populations. And so a lot of the work is going to be reliant on the calculator to get the information, but I'm going to show you the calculations that go into doing the traditional method and the p-value method. But realize that the work that we're going to do in the actual 7 steps, we're going to rely on the calculator, and that's fine. I'm going to show you how to go through the traditional method and the p-value method by hand, so that you understand where these numbers come from and why they are the numbers that we get, and how it works. Okay, because our point estimate, just like in Chapter 8, our point estimate is going to change, right, when we go to two samples. Okay, so just keep that in mind. Okay, so now, why are we studying two populations? Well, because it comes up a lot of situations where we want to compare either two population means or two population proportions. For example, drug studies, right? We want to see the effectiveness of one drug versus another, the efficacious, right? Efficaciousness. So is one drug more efficacious than another? So let's say we have a drug that that reduces cholesterol, right? And then the drug company comes out with another cholesterol medication they believe is better, right? So in that case, we might want to compare the two populations, say, hey, one population that takes the drug A and the other population takes drug B, and we do this experiment, right? And so we have a control group and two treatment groups, and we basically collect the data and see, hey, is the average cholesterol level decreased more with the new drug compared to the old drug? Okay, so that could be a two population hypothesis test. Another way of looking at it is comparing comparing two groups or two populations for exams, right? SAT scores. So we compare two populations, students who are on the general program and students on the, let's say, the college prep program, and see, we compare the average test scores for both groups and see, hey, does the college prep course group do better on average than the group of students who are on the regular general program? So those are the types of settings, and it can go in all kinds of industries, insurance, manufacturing. So that comes up a lot. So when we deal with two populations, it has a lot of applications in a lot of different situations. Okay. So now, with that being said, a couple of assumptions that we make, and it's going to be made for each one of these cases. The first assumption that we're making is that the samples from both populations are random. Okay, and that should be a no-brainer because we talked about random samples over and over again. So we're going to assume that the samples we get are random. The other assumption we're going to make is either both populations that the samples are coming from are normally distributed. Okay, so either that's the case, or both sample sizes from both populations are bigger than or equal to 30. And in that case, we don't care what the population is because we've got the central limit theorem applied to both populations, okay, or both samples. Okay, so we can get the sampling distribution of x1, let's say, and the sampling distribution of x bar 1 and the sampling distribution of x bar 2, and the central limit theorem for either one or both of them will tell us that they're approximately normally distributed. Okay, so those are the two assumptions we're going to make. Either both populations are normal, or both sample sizes are at least 30, okay? And if that's the case, then we can start talking about sampling distributions for what we're going to talk about is the difference between the sample means. We're going to start with the means first, okay? So again, remember in confidence intervals, when we dealt with two populations for confidence intervals, we had the same idea that, hey, if we look at the differences between them, okay? So that's what we're going to do. Oh, bless me. Okay, sorry about that. Okay, so here we go. So now here's the random variable. Let me get my markers. Okay, so here are some markers, and let me get my notes. Okay, so here is what we're going to use. So now, the idea is that we need, just like in hypothesis testing for single populations, where we need to know the distribution of the sampling distribution of our sample statistic, right? X bar or p hat. Well, the same is going to hold true for doing hypothesis testing for two populations. Just like in confidence intervals, we need to know the distribution of our point estimate, right? And once we knew the definition, or not the definition, the distribution of our point estimate, then we could construct a confidence interval. Well, the same thing goes for a two population hypothesis testing, okay? We need to know the distribution of our point estimate, of our test statistic in this case, right? That's what we're going to call it, our test statistic, our sampling distribution, okay? Now, here's the random variable. So if we're looking at the different hypotheses, so let's start with our hypotheses. So our hypotheses are going to look like this now, because now we're dealing with two populations. We're going to deal with two mu's, right? Two population means, right? So we're going to be dealing with this. We're going to have mu1 is equal to mu2 versus mu1 is not equal to mu2. So that's going to be 1. The second pair could be this. Mu1 is greater than or equal to mu2 versus mu is less than mu2. And then the final and third one is going to be either mu is less than or equal to mu2 versus mu1 is greater than mu2. So those are the three sets of hypotheses. So whether it's this one, or this one, again, is going to be determined by the claim. What is the claim in the problem, okay? And of course, we're going to notate which one is the claim parenthetically out in the margin here. And of course, we've got our two-tailed test, left-tailed test, and right-tailed test. Okay, so again, same thing that we talked about in chapter 9. Okay, so now, these hypotheses, now notice, we can rewrite these hypotheses in an equivalent manner. Okay, we could also write these same three hypotheses, these three pairs of hypotheses, like the following. We could say mu1 minus mu2 is equal to 0 versus mu1 minus mu2 is not equal to 0. And likewise, we can rewrite these other pairs of hypotheses in the same manner. Mu1 minus mu2 is greater than or equal to 0. Mu1 minus mu2 is less than 0. And then finally, we can have mu1 is less than or equal to, mu1 minus mu2 is less than or equal to 0 versus mu1 minus mu2 is greater than 0. So now why do I show you this? Because this is going to look familiar later on. typically either way is fine. I've seen the hypothesis stated this way or this way. Now in the textbook, this is the way that it is written, so that's the way we're going to keep it. But notice that all I'm doing with these is I'm subtracting mu2 from both sides. So mu2 minus mu2 becomes 0, and then mu1 minus mu2 comes over here. So these are equivalent statements. They're the same. Okay? So just realize that these are saying the same thing. Okay? They're equivalent. So now, with that being said, now let me show you the test, how the test works. Okay? So the first thing is the traditional method. Think about the traditional method. We have to calculate our test statistic, right? So when we're dealing with two populations, and again, we're dealing with the means, difference of means, right? That's why we're comparing, we're testing for the difference between means. Hence why this is also a good way to write it, because this is testing whether the difference is equal to 0, which means that there's no significant difference, versus it's less than 0, which means there is a significant 0. In fact, it's negative, okay? Versus no significant difference versus there is a significant difference and it's positive, okay? Versus the first one, which I erased, equals versus not equals, which means two-tailed test. It could be negative or it could be positive versus 0, okay? So now, well, we need, for the traditional method, we need our point estimate. Or not our point estimate, I'm sorry, our test statistic. So what's our test statistic going to be? Well, if, again, based on our assumptions, if x1 is normal, mu1, sigma 1, right? And x2 is normal with mu1 or mu2, sigma 2, right? If this is true, okay, or if my sample sizes are big enough, which means n1 is bigger than or equal to 30, and n2 is bigger than or equal to 30, okay? If either one of these is true, then I know the sampling distribution of what? It's going to be x bar 1 minus x bar 2. Now, I'm not going to derive this because, again, it's not, it's beyond the scope of this class. It's not necessary to derive this, but we can prove this by knowing this or this. So if we know that the populations are both normal or the sample sizes are bigger, we're going to know what? We know that from chapter 7, right? From chapter 7, we know if this is true or if this is true, then we know that x bar 1, right, the sampling distribution of this population, of this sample, x bar 1, is going to be approximately normal or normally distributed with a mean of mu1 and a standard deviation of sigma 1 over the square root of n, right? And we also know from this or this that x bar 2, the sampling distribution of the sample mean of population 2, is going to be approximately normal with a mean of mu2 and a standard deviation of sigma 2 divided by the square root of n2. So this should be n1. So again, this should be of no surprise. This should make complete sense based on what we've talked about in chapter 7, right? So this or this gives us this, right? So this gives it to us using the central limit theorem. This gives it to us because if the population is normal, then everything is normal. X bar is automatically normal, regardless of the sample size. And likewise, the same thing holds for true in over here. Okay, so in either case, we know this. Well, if these two are true, then it can be shown that the difference of the two sample means is also normally distributed. And what happens here is this. We know that x bar 1 minus x bar 2 is going to be approximately normally distributed with, guess what? The mean of this random variable, right, is going to be mu1 minus mu2. And now here's where the tricky part comes in, and I'm not going to derive this again. It's unnecessary for the scope of this class. But what about the standard deviation of x bar 1 minus x bar 2? What does that turn out to be? Well, if it turns out to be the sum of the variances square rooted. So we take the square root of the sum of the variances. So we're going to take the square root, and we're going to take the variance of population 1. So that's going to be sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. And so that's going to be the standard deviation of this random variable, x bar 1 minus x bar 2. Now, again, I'm not going to derive this. This is something we're going to use and just need to accept. But again, we know from chapter 7 that if this or this is true, then we get both of these. And it follows that if both of these are true, then we get this, okay? And so this, let me use a different marker. This is what we're going to use in our 7 steps of our hypothesis testing. So when we calculate our test statistic, or we calculate the p-value, it's going to be based on this distribution, okay? So again, basically what we need is if both of these are true, right? If both populations are normal, okay, then we automatically get this if we're dealing with the difference of means. Or if our two sample sizes are at least 30, then we also get this, okay? So just keep that in mind. Same conditions as when we were dealing with confidence intervals for two populations, okay? And so this ultimately is the sampling distribution for the difference of two means, okay? Two sample means. So now, with that in mind, let's calculate the test statistic that we would use for this hypothesis test. Okay, so now I'm going to erase this. And so now let's calculate our test statistic. And in this case here, now notice that we're assuming, right? Assume sigma is known. Okay? So we're going to assume sigma is known in this case, and then we'll deal with when it's not known. Okay? So in this case, if sigma is known, we're going to be dealing with a z star again. Well, how do we calculate our critical value, or not critical value, our test statistic? The same way we do before. We use the z-score formula. Okay? So now in this case, it's going to be, again, observed value minus the mean divided by the standard deviation. Well, now, what does that look like now? Well, what's the observed value? The observed value is going to be the difference in the sample means. right? So that's going to be based on our observed samples. So the observed value is going to be the difference between x bar 1 minus x bar 2. So that's going to be based on the observed data. Now, minus the mean. Well, what's the mean? We're talking about the mean difference, right? We're talking about the true difference between the two populations, which is mu1 minus mu2. Now this brings up the question of, okay, well, what mean are we going to use? What are those going to be? This is where the equivalent form of these comes in. Because remember, we're always going to assume what? The null is true. And since we're always going to assume the null is true, that means we're going to assume that there's no difference between mu1 and mu2. So what does that mean? Well, if there's no difference between mu1 and mu2, then we're saying that they're equal, right? And if mu1 is equal to mu2, what's the difference? 0. So under the null hypothesis, for all three of these pairs of hypotheses, we will always assume the null is true, and which means that we're going to assume the difference between mu1 and mu2 is 0. So what happens? This is going to be mu1 minus mu2, and under the null, this will always be equal to 0. And so it'll always drop out, okay, so in our calculation. And then, of course, the standard deviation is the standard deviation we just derived, or at least I showed you what it is. And that's going to be the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And so, lo and behold, what we end up with is just this, because this goes away. So in the end, all we end up with is our test statistic formula is going to be x bar 1 minus x bar 2 divided by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And so this is the formula that we will use for the test statistic involving the testing of two means if sigma is known. And it's going to be a z star. Okay, and I hope that makes sense. Okay, so now, this is how we calculate our z star. Now, the thing is if we do the traditional method, all we have to do is compare it to our significance value. Well, what's the significance or the critical value always based on? Alpha. So again, our method of getting the critical value isn't going to change at all. We're going to look at alpha, and we're going to either use the table to get our z-score, the z-critical value, the z-alpha, or the z-alpha divided by 2, depending on what test you're running. Or you're going to use inverse norm on your calculator. So when it comes to the critical value, in this case, it's exactly the same as what we've been doing before. Not going to change, okay? You just have to remember what the area to the left of your critical value is, right? That's going to be determined by the test, right? Because the test is going to tell you which tail is alpha, if both tails are have alpha or not, okay? So in that case, it's going to be very easy to figure out. So the only thing you really have to remember is your z star, okay? So getting z alpha or z alpha divided by 2 is the same as we've been doing before, okay? So now, enough about that. Well, the p-value method. What about the p-value method? Well, the p-value method is going to be the same way, okay? The p-value method, so we're going to calculate p-value. Let's let's use this one here, so a left-tailed test. Again, just be careful. The same rules apply, the same cautions apply in this case when you're dealing with p-value. Make sure that if you're doing a two-tailed test, when you calculate the area in one tail, depending on what your test statistic is, right? If it's negative, you got to go to the left tail. If your test statistic turns out to be positive, you're going to go to the right tail. But whatever area you get, you have to double it for a two-tailed test. Okay, so just be careful. And make sure you use alpha divided by 2 in a two-tailed test, right? Half of alpha goes in one tail, half of alpha goes in the other tail. Don't forget that. Okay, so let's do the left-tailed test. And so to calculate p-value, this is the way we're going to do it. So p-value, again, is the probability that your test statistic is as extreme or more extreme than the value that you got. Okay, so what determines the direction of which way you're going? The test. Okay, to left-tailed test, you're going to the left. Okay, so it's going to be this. You could do this. Just like we did before, we could test the probability that your sample statistic, right? That's x bar 1 minus x bar 2, right? We could say the p-value is equal to the probability of being as extreme or more extreme than the value that we got from the sample. So it would be less than or equal to whatever we got, right? Less than or equal to because we're considering a left-tailed test here, okay? Now, when you do this, you have to know what you're putting in the calculator for the mean and the standard deviation of the distribution. Which distribution? The sampling distribution. So don't forget about the sampling distribution. So as long as all the conditions are met, we know the sampling distribution of x bar 1 minus x bar 2 is as follows. It's going to be normal with a mean of mu1 minus mu2, and then the standard deviation is the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. So now, if we're going to use this, then when we use normal CDF, because if it's normal, we can use normal CDF to get our probability, right? So normal CDF, we just need to make sure that we put in the correct lower bound, of course, right? The correct upper bound, right? But the most important thing is, what is the mean that we're going to put in? Well, the mean is always going to be under the null hypothesis. Well, what's the null hypothesis? That there's no significant difference. So remember, it's going to be 0. So with normal CDF, this will always be 0. Now, the standard deviation, remember, this is the standard deviation you have to put into the function. So you have to make sure that this is what you put in for standard deviation. Okay? So that's one way to get the p-value. Okay? Just make sure you do that. Now, the way I would do it is I would just go ahead and calculate the z-score and use the z-score, your test statistic z-star, in the probability. Because remember what we talked about in Chapter 3 about percentiles and z-scores and probability. If you have a particular value, the probability of being less than or equal to that statistic in your sample, as long as we know it's a normal distribution, will always be the same as the probability of being less than or equal to the z-score that corresponds to that value. So it doesn't matter if we use this or if we use z-star, it'll give me the same p-value. So I could do it this way, where I just use this and find the probability of being less than the value that I got and just plug in the correct information. I could do it that way. Okay? In fact, I encourage you, do it both ways and prove to yourself that it does give you the same answer. Okay? Now, so this is one way. The other way is just to, instead of using this, just calculate your z star and use z star. So my p-value is also going to be equal to p, that the probability that my test statistic z star is less than or equal to whatever value that I got. Well now, since I'm dealing with a z star value, now I can use normal CDF, and I don't have to worry about calculating and putting all these complicated looking things into my calculator. It's just it's a standard normal curve with a z-score, right? So if I already know this, then I already know what my mean and standard deviation is. It's going to be 0, 1 every single time. So all I have to do is put in the lower bound, right? Normal CDF. Put in the lower bound, followed by the upper bound, and then since I'm dealing with a z-score, it's a standard normal curve. So the mean and the variance, or excuse me, the mean and the standard deviation are always going to be the same, 0, 1. And I'm done. So this is the p-value method. Then once you get the p-value, then you just compare it to alpha and you're done. Okay? So that's the idea. So now, let's do an example. Okay, let's pick an example here. Okay, it says, for this example, it says the mean lasting time of 2 competing floor waxes is to be compared. The amount of time that each brand lasts is normally distributed. So we know the population of each brand of wax is normally distributed. So that's that's the assumption we need, right? We also have random samples too, because it says each brand of wax is applied to 20 randomly chosen floors for testing for how the finish lasts under normal wear. The data are recorded in the table below. Okay, so we've got both of our assumptions are met, so we're good to go here. Okay, so we know that the sampling distribution for x bar 1 minus x bar 2 will be normally distributed. Okay, so we've got that. Okay, so now it says using a 5% level of significance, does this data suggest that brand A wax lasts longer on average than brand B? So now here's the thing. One of the key things, because since we're dealing with 2 populations, we have to decide in the beginning which population we're going to consider population 1 and which population we're going to consider as population 2. Because once we decide that, then that's going to help us, that's going to determine which one of the 3 pairs of hypotheses that we're going to use. Okay, because if we switch them, it's also going to affect which alternative hypothesis we need to use. Okay, and you'll see that in a minute. Okay, so now let's use this. So they're looking at brand A and brand B. So let me show this. So first of all, we have to decide, okay, which one is going to be population 1, which one is going to be population 2. So let's make population 1, let's make brand A population 1, and let's make brand B population 2. Okay? So the claim here, so make sure I didn't write, yep, I wrote too high. Okay. So let me, you're right here. So let me go, the claim. Okay. So, okay, so you can, I think you can see that. Yeah, so that's the claim. And the claim is what? Brand, oops, not band. claim. Brand A lasts longer on average, key word, on average than brand B. Okay? Now, we decided that brand A population, right? So population 1 is going to be the length of time that brand A wax lasts. Okay, so that's going to be where we're going to get x1. So that's going to be mu1, right? And then mu2, the second population, is going to be the population of times that brand B wax lasts. So that's going to be where we're going to get x2, right? The distribution of x1 and x2. So we're going to make this, these times mu1, and these times, right, the times that brand B lasts, mu2. And so it says on average that mu1, brand A, lasts longer, right, than. Well, lasts longer than would be greater, right? A greater time. So now we know what our alternative hypothesis has to be. So that means as we set up our hypotheses, right, step 1, our alternative is going to be mu1 is greater than mu2 versus the null, which is going to be mu1 is less than or equal to mu2. And the claim is the alternative in this case. Okay, so far so good? Okay, good. Now, this is going to be a right tail test. So now again, step 2 is always the same. We're going to assume the null is true. So in other words, we're going to assume that mu1 is equal to mu2. And in fact, this is always going to be our assumption. Okay? In other words, mu1 minus mu2 is equal to 0. Okay? Hence why when we calculated our test statistic z star, we left it out. It dropped out, right? Okay, so now step 3, we're going to put in our data. So alpha was what? Alpha, they said 0.05, 5% significance level. So alpha is 0.05. And now the data, here's the data. This is where we're going to put the data. So here's our table. So now, so here's A and B, and here's X bar and sigma. Okay, so X bar 1 is equal to what? 3 months. X bar 2 is equal to 2.7 months. Standard deviation 1, so sigma 1 is equal to 0.33, and sigma 2 is equal to 0.36. Okay, so there's the data. Okay, so now, here's where we're going to do our testing. So now, first thing is what's the sample sizes? So let's do this. So n, what was n? n1 was equal to 20, and which was also equal to n2. So the sample sizes are both the same. Now, this normally would be an issue because the sample sizes are too small, but they also tell us that x1, the distribution of lasting times for wax A was normal, with mean mu1 and standard deviation of 0.33. And they also tell us that the distribution of lasting times for brand B is also normally distributed with a mean of mu2 and a standard deviation of 0.36. So now what this tells us is that we know from this data, right, from this here, that we know that x bar 1 minus x bar 2 is also normally distributed with a mean of mu1 minus mu2 and a standard deviation that's equal to the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And so that's what we're going to use for step 4. Okay? So now in step 4, let's use the traditional method first. So we're going to calculate our z star. So that's going to be, again, under the null, the differences are 0, okay, between the means. So this is going to be x bar 1 minus x bar 2 minus mu1 minus mu2. But of course, because under the null, this is 0. So that's going to drop out. And then this is going to be the standard deviation for both populations. So it's going to be sigma 1 squared over n1 plus sigma 2 squared over n2. And so now if we plug and chug, well, what do we know? We have the information right here. So x1 is 3. So this is going to be 3 minus 2.7 divided by the square root of, well, here are the standard deviations. So it's going to be 0.33 squared divided by n1, which is 20, plus 0.36 squared, also divided by 20. And so now what I'm going to do is I'm going to put this in my calculator, and I'm just going to compute my test statistic z star. So 3 minus 2.7 is 0.3. And now divided by the square root of 0.33 squared divided by 20 plus 0.36 squared divided by 20. And so I get 2.75. So my critical value is 2.75. Okay, or not my critical value, I'm sorry, my test statistic. Now, if I'm doing the traditional method, I now need my critical value, which in this case is a right-tailed test. So it's going to be z alpha. And so alpha is the area in the right tail. So my area to the right is 0.05, which means the area to the left is 0.95. And that's what I'm going to put into inverse norm. So inverse norm, 0.95, comma 0, comma 1. And so what do I get? Well, I'm going to get my common z-score that you guys hopefully are starting to realize. My z-score here is going to be 1.645. That's going to be my critical value. So now, because it's a right-tailed test, I'm going to reject the null if my test statistic is greater than or equal to my critical value. And in this case, it is. So my test statistic is greater than my critical value, and therefore I reject the null hypothesis. So now let me just state this so I can give some room. So then again, after that we do 5, right? So 5 is based on what we just did. 5 is my z star, which is equal to 2.75, and my z alpha, which is equal to 1.645. Well, this is definitely bigger than or equal to my critical value, right? So 6 is, again, we reject the null. So what does it mean for our claim? Well, what are they claiming? They're claiming that brand A wax lasts longer on average than brand B. Well, we reject the null, which means that there's evidence to support the alternative, and the alternative is the claim. So there is strong evidence based on the sample data and an alpha level of 0.05 to support the claim that the lasting time, right, or that brand A wax lasts longer on average than brand B. And that's it. So that's how you do the test. Same 7 steps, okay? Now the p-value method, here's what I'm going to do. It's a right-tail test. So the p-value method, I'm going to go back here to step 4, and I'm going to calculate the p-value based on the fact that it's a right-tail test. So p-value is going to be the probability that my test statistic, z star, is bigger than or equal to than what I got based on the sample, right? So this is going to be greater than or equal to what? Well, 2.75. So now what I'm going to do is I'm going to use Normalcdf. My lower bound in this case is 2.75 because it's greater than or equal to here. So my minimum value is 2.75, and then my maximum value I can just put in 10 to the 99th power, right? And then following that, I can go ahead and put in the mean and standard deviation, and I don't have to calculate anything because it's a z-score, so it's always going to be 0, 1. So I just put in 0, 1. And now I'm going to go to my calculator and see what I get. And I get 0.0030. 0.0030. And so again, now I'm going to compare p-value to alpha. And of course, p-value of 0.003 is definitely less than 0.05. And so we get the same result, we get the same conclusion, and that's it. Now, let me show you the function on your calculator that you will use to do this. And this is the way I'm going to do it from now on, because this is the way I'm going to expect you to do it on a test. But again, realize that you can get the same answer using each method separately. But I'm a fan of the calculator as long as you understand the concepts. So here is what we're going to do. Here's the function that you're going to use if you're dealing with a 2-population hypothesis test and for the means, right? So this is specific for population means. So you're doing a hypothesis test for the difference of means, and both sigma 1 and sigma 2 are known. So the population standard deviations are both known. Okay? If that's the case, then the function on your calculator is going to be 2 samp z test. 2 sample z test. Okay? So as opposed to the 1 sample z test, which is just z test. Okay? So now, Again, you're going to have to choose data or statistics. In this case, we are given statistics. So you're going to put in, and it's going to ask you for more information, right? So it's going to ask you for the null hypothesis again. It's going to ask you for whatever. Well, actually, it's always going to be 0. So it's not going to ask you for anything for that. So on the 2-sample z-test, it's going to ask you for the following information. And again, you can go to the calculator and actually look this up too. And so it's going to ask you for what your input is, right? In other words, are you going to use data or stats? Here we're using statistics. And then it's going to ask you for sigma 1, sigma 2. It's going to ask you for n1, n2. And it's going to ask you for x bar 1 and x bar 2. And then it's going to ask you for the alternative hypothesis. So you got to put all of that information into the calculator. So I'm not going to do that. Okay? But if you plug all the information from step 3, so you're going to have x bar 1, x bar 2, sigma 1, sigma 2, n1, n2, and then you need to know what the alternative hypothesis is. The null hypothesis will always be the same. It's going to be 0. So it's not going to ask you for that because it's always 0 when you're dealing with 2 populations. Okay? So anyway, you put that in there and you put it in your calculator, and what you get is you get a z-score of the following. Now, again, they like to put typos in here, so let me do it. So stats. I'm just going to put in the calculator. Signals 0.33. Sigma 2 is 0.36. X bar